Hello, everyone. Um, Thanks for having me here. And today I'm going to try to give you a little glimpse into research in pure mathematics. So I'm going to talk about certain work that I did with my collaborator, Jonas Hartwig, who is at Iowa State University. So most people might be familiar with the name Heisenberg. So maybe because you've seen the TV show Breaking Bad, or maybe because you've heard of the uncertainty principle. Well, as you might have guessed, the second one is the thing I'm interested in for today. So the uncertainty principle in quantum mechanics is an important principle that tells you that there's some sort of fundamental limit in how precisely you can measure at the same time the position and the momentum of a certain particle. Okay? So if you are more precise measuring one of those two quantities, then you cannot be as precise measuring the other one, and vice versa. Okay, well, there's several different ways to express this mathematically. One possibility, if you choose the appropriate conventions, is the equation that PQ minus QP is equal to 1, where P represents the position and Q represents the momentum of the particle. Now, this equation doesn't really make sense if P and Q are numbers, because multiplication of numbers is commutative. So PQ should be the same as Q times P, and the difference should be 0, and cannot be equal to 1. So clearly, we need to do something different, and mathematicians did. And so they invented this new algebra where this works, and this is called the Weyl algebra from the mathematician Hermann Weyl. So these are the sort of things that I study. I specialize in abstract algebra, so we study new ways to do operations and try to understand what those new ways to do operations represent. So now we can take the rules for Weyl's algebra and we can change them a little bit if we want. And this is the sort of the beauty of pure mathematics, is that we are not constrained by what actually works and makes sense in the physical universe, but we are only constrained by whatever works logically in our own mind. So we can take Weyl's algebra's rules and change them a little bit, and we get what are called twisted generalized Weyl algebras. And those, well, since we change the rules, do not necessarily represent actual physics theories like quantum mechanics, but we can still study them mathematically. So in 1999, mathematicians Mazurchuk and Turovska defined these. And so as I was saying, we still need to make sure that our definitions make sense. And what they found is that in order for things to make sense and work logically, they needed two numbers, a and b, and they needed two functions, f of x and g of x, such that they satisfy this consistency equation that f of x plus a times g of x plus b is equal to f of x times g of x. So then the question becomes, if you're given two numbers a and b, what are all the possible functions f and g that satisfy the equation, right? So this is what's called a functional equation, because the unknowns, the things we're trying to find, are those functions f and g, okay? And so as it so happens, my work with Jonas is that we found all the possible solutions to this equation. And the way we describe those solutions is by drawing paths on a grid that wraps around the cylinder. So this might sound weird, so it's going to be better explained by looking at some pictures. So, all right, here's two pictures of cylinders that correspond to different choices for the numbers a and b. So for each choice of number a and b, you're going to get a different kind of cylinder. Notice that the numbers have to be, one of them has to be positive, the other one has to be negative. If they're both positive or both negatives, things are not going to work. You're not going to get any solutions. And so the other things you can notice in this picture is that the grid that wraps around the cylinder, the lines on the right, they're steeper, more vertical than the ones on the left. And that corresponds to the fact that the numbers a and b are higher in that case. So that's going to be sort of a general thing that happens. All right, so then how does the solutions to the equation work? the way it works is that you need to choose a starting point. So your starting point is going to be an intersection point from the cylinder. So it's going to be a point where a blue line and a black line intersect. And from that, you're going to move on the grid, either move along a blue segment or a black segment until you get to a new intersection. And then you keep doing that while wrapping around the cylinder. You have to keep going the same direction. You're not going to backtrack, so you have to always go counterclockwise, for example. And if after doing that, you go back to the point you started from, then congratulations, you found a solution to the equation. Then here's two examples. All right, so 2 examples I've drawn in red the path. So you can see that those are paths that you start from a point and then you wrap around and eventually you get back to the point you started from. And so those 2 pictures represents 2 solutions to the consistency equation. So we have a method in our paper that tells you how to translate this picture into the functions f and g that solve the equation. And so then each of these pictures then represents a new twisted generalized Weyl algebra. Now, I'm not saying that if you just take a piece of paper, you draw a picture like this, then you've defined automatically a new theory of quantum mechanics. But I'm also not saying that you did not define a new theory of quantum mechanics. For sure, to be sure, you'll have to ask a physicist. All right. Well, thank you.